okay, we want to see if we just use this strategy, can we come up with an algorithm which efficiently computes the gradient for one general MLP. And by MLP, I simply mean this fully connected feed-forward neural network. So can we do this? And you can guess that we can simply do it, but what I want to do here in this part of the course is to give you a bit of idea how these gradients are propagating over the network, how you can think about it. I mean, there are too much derivations here, and I don't expect that you follow all the details, so I just try my best to give you the intuitive illustration so that you see it. If you're very interested, you can go through the details step by step. But the key point that I want to give you here is that you see if you're seeing one neural network, you need to start after this course, you need to get this capability to look at the neural network and be able to understand where the gradient is propagating, where is the problem. Like if it's not getting trained, you don't have gradient, where is the bottleneck where you can figure it out and fix it, okay? So let's start with this MLP. And for the MLP, since everything is simple, we can do it with more details. What I want to do 3 local operations. This is a kind of terminology I made by myself. This is the easier way that I could understand the whole algorithm. So what is a local operation? I assume that I have this particular function, r hat, and r hat here is a scalar function. So I really wish that I was in the other lecture hall where I can write and show you the slides together. But today I'm unlucky, so I'm going to keep it a bit up so that I could use the board right now. So what I think that I have this particular function r hat. And this function r hat is a scalar function. It means that it gets a vector as input, but it's going to return scalar value as output, right? So this is indeed, for instance, your loss function, right, in the neural network. And what I do know that, so I have this particular y here. So this y is in general k-dimensional, okay? So I assume this guy is k-dimensional. So it means that y, for me, I'm going to write it here, y for me is one vector which has k different entries, right? And now this guy is passing through some process, so it could be a loss function or whatever, you don't care. And then this is giving you r hat. And this r hat is just one-dimensional, right? So it's a scalar. This guy is a scalar. Right? Now, the thing is that what I do know what is the gradient of r hat with respect to this particular variable y. What is this gradient? What is the dimension of this guy? It's again k, right? So the gradient of r hat with respect to y is going to be, again, a k-dimensional thing, right? So this guy is k-dimensional. Now, what I'm going to do, I am going to think of no color, okay? I'm going to think of another variable here, right? So this variable, I'm going to change it. I'm going to consider different kinds of variable. This variable, with some specific sort of transform, is transformed to y, okay? So it could be another vector, passed through some function, gave me y. It could be a matrix, again, passed through a function, gave me y. It could be a scalar, passed through a function, gave me vector y, okay? So I assume I have a variable here is passing through one function, gives me y, and then this guy is giving me r hat. What I do know the gradient of r hat with respect to y. What I want to know whatever the variable here is. Say this is z. I want to know what is the gradient of r hat with respect to z. Okay? Everybody's clear what I'm doing? Now, if I want to do that before we start anything, how can I compute this one using chain rule? What is the gradient of r hat with respect to z? How can I write it down if I want to use chain rule? And you forget about what kind of product you need. Just forget about everything. Think of z, y, and r hat, all of them being scalar. What do you do? I need gradient of r hat with respect to y, right? Multiplied, I should figure out what this multiplication is, right? Times gradient of y with respect to z, right? And again, I need to figure out what is this gradient, right? So these are things that I need to figure out, but if I figure out this stuff, it doesn't change the fact that I'm using chain rule, right? So I get from this guy here, and then from this guy, again, I compute the gradient of y with respect to z, right? And this gradient could be different object depending on the kind of z and y that I have, right? Everybody's cool? So you got the idea what I'm doing now? OK. Now, let's start with these operations. So this is the problem that we have. So the problem that we have this particular r hat. This is passing backward to y. So I do know the gradient of r hat with respect to y. This is what I know. Now I'm going to replace different kinds of z here. And then I want to know what is the gradient of r hat with respect to z. I am obviously using chain rule. The whole thing is that I want to see how does this chain rule look like, and whether we can develop a bit of intuition that we always understand the chain rule on the computation graph. OK? OK. So let's consider the first case. The first case that I'm considering is that z, which is just generating this y, this z is one k-dimensional vector, so it's exactly same dimension as y. Y is k-dimensional, z is exactly k-dimensional. And every single entry that I have in y is f of z, right? So this z is just passing entry-wise through one function f, and it's giving me y. What kind of process does it in neural network? Activation, right? So in neural network, you compute your z, your soft information, right? And then you activate it. And when you activate it, you just pass every single entry through function f, right? So it's the same thing. So I assume z is the same dimension as y, and then I want to know how I can figure out the gradient of r hat with respect to z. Now, I am going to show you the details, but before doing it, let's do it once together. So can you tell me what is, like if you want to take the derivative of y with respect to z? Can you tell me how you can do it? Say you want to compute and think about, like, right now, think about y and z to be scalars, right? So I want to compute derivative of y with respect to z. What is it? So I do know that y is f of z. Then what would be this guy? F, right, exactly. So you're going to be f prime computed at the same point z, right? So I can write it down f dot, right? Now, if every single entry is computed with the same approach, how can I make a gradient for this one? How can I write the gradient of y with respect to z? Can you give me a suggestion? A vector, exactly. So I can write down a vector. And what are the entries here? A derivative of every single guy, right? So I'm going to put f dot of z1, f dot of z2, and so on till f dot of the last guy, right? This is going to be the gradient, right? So what is the dimension of this gradient? K, right? OK. So I have this guy now, right? And this is a k-dimensional vector, right? Right? OK. What is this guy? Again, we talked about it. It's k-dimensional, right? So this guy is also k-dimensional. Now, what about this guy? What is the gradient of r hat with respect to z? Why should it be a matrix? No, think about this here. You have r hat is a scalar function, right? And then it's coming from z. If you compute gradient of r hat with respect to z, forget about all of it. Y scalar? This is a vector, right? This is k-dimensional, right? This is a k-dimensional thing. Look at whole thing here. as one shot process. So say that Z, which is a vector of k dimensions, is just giving you in one shot r hat. And you don't care what is happening in between. It's a process, right? Now you want to compute the gradient of r hat with respect to z. What should it be? It's a gradient. It's a k-dimensional vector, right? So you're going to have gradient of r hat with respect to z, which is partial derivative of r hat with respect to the first guy till partial derivative of r hat with respect to the last guy, right? Everybody's cool, right? So now, okay, get back here. So this guy should be, again, k-dimensional, right? Yes? Technically, if you want to be very precise, you shouldn't show it like this. You should show it as a diagonal matrix, and then it's going to be a Jacobian. But we don't want to talk about this that way. We're talking computational. This is whatever you need, right? You can show it this way, right? And on your computer, you can save it as a list, right? So you can do it whatever you want, right? Okay. So, but if you want to be mathematically concrete, then you should say that this whole vector is again a giant function, and that giant function is taking k-dimensional to k-dimensional, and then you have a Jacobian. We're going to do that for a general function later, but right now we don't need it, right? No. Now, this guy is k-dimensional, right? This is k-dimensional, this is k-dimensional, this is k-dimensional. What kind of product can take two k-dimensional vectors and give me one k-dimensional vector? Any idea? Entry-wise product, right? So I'm going to do entry-wise product. I get every single entries and multiply them, right? K-dimension, k-dimension, k-dimensions, right? Everybody's cool? So you can go ahead and do the math, and you're going to see that you're going to end up with exactly same expression. So if you, for instance, want to know what is the gradient of r hat with respect to one entry, derivative of r hat with respect to one entry of z, you would write it down r hat with respect to entry of y, which is giving z, times partial derivative of r hat with respect to z, right? And then this one particular guy is going to be the partial derivative with respect to y, which you have. So this is the entry, particular entry in your gradient of r hat with respect to y, times f dot of z, right? So if you show the whole thing in this form, so this is f dot of the whole vector. This is exactly the vector which we defined here. This is right now behind the screen. So, but it was like a collection of the derivatives. Then you just do entry-wise product, right? But you don't really need to write down all this math here, right? So you can simply say, I need to do a chain rule, right? And I do know this is the derivative of y with respect to z. This is the derivative of r hat with respect to y. I need to figure out how I can combine these two in a product form to end up with that particular gradient that I want. And of course, there's no way but doing the entry-wise product, right? You see it? So again, like what I told you last time, typically in practice, this is going to be done by PyTorch, right? But the thing that you need to know here is that, well, this is how PyTorch is going to do it. So if I don't see training, if I don't see gradient, maybe I can figure out, maybe there is a problem with this f dot, right? Maybe there is an issue here. Because if this guy is 0, then it's going to make the gradient of z 0, right? So there is no gradient going back anymore. Everything stops, right? So this is the key point you need to know, right? But very detailed version of writing it down. I mean, you can always do the math if it's necessary, but you can see it, right? As long as you can see it, that's enough. Okay? So moral of the story, if you have r hat, and you compute this gradient of r hat with respect to y, you can move backward through this process of just entry-wise operation by just computing the derivative and multiplying it entry-wise with the gradient of r hat with respect to y, right? And by entry-wise product, I simply mean, oh, I forgot equal here. Okay, so typo here. It should be equal to, I mean, you just multiply every single pair of entries, right? Everybody's clear? Questions? Yes? What is a matrix? Why should it be a matrix? Okay. But what kind of product you're doing? I mean, r hat, I mean, as I told you here, r hat, this one. No. So you can, I mean, you don't care about how r hat is computed. R hat is computed out of z, right? So you can write down r hat to be one function. I don't know what is that function. One function of z. And z has k entries, z1 till zk, right? And now if you want to write down the gradient of r hat with respect to z, it cannot be a matrix, right? It must be a vector, right? So you don't care how it's coming from. Because if I have two vectors, I can multiply them to become a matrix. I can multiply them to become a scalar inner product. I can multiply them to be a vector. Or I can even do some weird other kind of product to just change dimension, right? So I can come up with any sort of product, and all of them are products, right? So you cannot say for sure that when I have two vectors and I mean, theoretically, having two k-dimensional vectors, you cannot simply multiply them, right? You either need to just transpose one of them to have an outer product, and it's going to give you a matrix. You need to or transpose the other one, multiply them, is going to be a scalar, right? Or you can do whatever I said, right? So the kind of product is now on your choice, right? And then it could change. But what you know is that you definitely want to end up with a vector, right? And since you want to do that, so it's going to specify what kind of product you need, right? Okay. Okay. So now let's go for the next operation. So the next operation that we want to talk about is this one. So what we do have here, we have r hat, right? And it's coming from y again. So again, this part is exactly the same as before. Now what I think instead of having zk dimensional passing through one entry-wise function, I assume that z is an n-dimensional. So n is no different from k. And it's just being transformed linearly by some matrix A to y. Okay? So x is n-dimensional, y is k-dimensional. What should be the dimension of A, this matrix A? I have written it here, but you can see. So if A gets multiplied to z and gives you y, then the number of columns in A should be exactly the size of n, which is size of z, which is n, and the number of rows should be size of y, which is k, right? So A is k times n, right? So it's going to get n-dimensional vector. It's going to linearly transform it into n-dimensional vector, right? Okay. Now, right now, what I want to do, I want to repeat whatever we did before. So, but with one difference here. So, first of all, you tell me if you have this gradient, if you compute this gradient of r hat with respect to z, what should be the dimension? So z now is n-dimensional, right? This guy is now n-dimensional. And of course, it's linearly transformed. After the linear transform, it's going to be transform again to get into r. But you don't care about that, right? So you say z has passed through some functional operation ending us up with r hat, right? So r hat is a scalar, z is n-dimensional, so this is going to be function of n variables. And what's going to be this gradient? What is the size of this gradient? N times 1. So it's a vector n-dimensional, right? Cool. Now, this is one thing. The next thing is that y equals to az, right? Now, if y equals to az, right? Yeah. And then if y is az, and you think again about everything to be a scalar, what is dy dz? What is it? If everything is scalar, what is the derivative of y with respect to z? It's going to be a, right? Correct? Now, if you want to have the gradient of y with respect to z, then in the matrix form, what do you expect? It should be, again, the matrix A, right? So because this is a linear transform, in the scalar case is the slope of that transform. In the matrix case is, again, going to be a slope of that transform, which is now a matrix, right? So this gradient should be proportional to A, is a kind of A, right? So A should show up there. And now we're going to get here, now we have this gradient. Now this gradient is now A, right? And what is the dimension of A? Now, what about this guy? This is gradient with respect to y is the same thing. This is k-dimensional. What should be this gradient now? What is it? N. So how can you multiply a k-dimensional vector with a matrix and end up with an n-dimensional vector? Exactly. So you could say that I have this A, which is k times n. I want to multiply it by k times 1 vector, right? And this guy is a k times 1 vector, right? And then if you want to multiply these two guys, what kind of product you need? You can simply write it down, A transpose times gradient of r hat with respect to y, right? This is going to be n-dimensional, right? This is what you want. Everybody sees that? Right? So again, you don't need to do the math. You can simply say that the gradient of y with respect to z is definitely A, or something like a transform of A, right? Maybe transpose, maybe whatever. But it's A, right? It's proportional to A. The information here, the gradients here, are the entries of A, right? And this gradient is also k-dimensional. The only thing I need to figure out is to find out a way to multiply this A to this vector to end up with n-dimensional vector. So the only way that I can do it, that I just multiply A transpose with gradient of y. Everybody sees that? Everybody's cool? OK. Now, again, what I want you to see here is that, for instance, if you see a linear transform, if you see after this linear transform, your gradient is becoming 0, what you can understand based on this thing that we did here, you would say that, OK, there is a problem with that matrix A. Maybe that matrix A is completely 0, right? Or maybe it has 0 exactly on the wrong places, which makes the gradient not going backward, right? Questions? Everybody's cool? So you can go ahead and do the math. So you can say that y, one particular entry of y, is written in terms of the whole entries inside z in this form. So essentially, you get one row of A and multiply it with z, right? This is going to be your y. And then you can start writing down the chain rule. But of course, the chain rule here is the vectorized form, right? So you're going to say that the gradient of r hat with respect to zn is going to be gradient of r hat with respect to every single y that I have times the gradient of that y with respect to the corresponding z, right? And if you do this summation, you're going to end up again with a column of A, right? Which is going to end you up with this form. So you're going to say one entry of this gradient with respect to z is going to be A transpose, the corresponding row transpose, times the gradient of y, which means that the gradient of r hat with respect to z is A transpose gradient of r hat with respect to y, okay? So you can do the math always, but as I said, if you see, I mean, you can immediately see it if you just compare the vectorized form with the scalar form, and then you can always figure out what kind of product you need in order to just keep the dimension correct. Everybody's cool? Questions? No question? OK. So yeah, this is the same argument that I showed on the board. So if you want to change the dimension from k to n, obviously you need to have that A transpose multiplied with the gradient, and that is quite obvious. So what you do always, so if you have such a transform, so here you have your gradient, and then whatever this gradient is, you're going to multiply it with A transpose. Now you have the gradient with respect to z. And you can keep on going backward, right? OK. Now, let's do one last thing. And the last thing that I want to do is to just replace A and Z. OK? So what I think now is that this variable here, I mean, still y is A times x. Now, instead of z, I'm writing it down x. So this y is still coming as A times x. OK? But now my variable is not the vector, it's the matrix, right? So I want to know what is the gradient of r hat with respect to A. Now, first of all, what kind of operation it would be? What is A in a neural network then? Weights, exactly. And what is X? Is, for instance, data, right? Or whatever the last layer has given me, right? So you get whatever the last layer gave you, or your data multiplied with a weight vector, and then you compute the next layer output, right? So I want to know if I have computed already gradient up to y, and I want to just move backward to the weights, what is the gradient with respect to the weights? This is actually what we need to compute at the very end, right? Because we want to know the gradient of our loss with respect to the weights inside the neural network. Everybody's clear? OK. Now, everybody is cool. What is the gradient with respect to a matrix? If you have a k times n matrix, what's going to be the gradient of r hat with respect to that matrix? What is the dimension of that object? It's a k times n, exactly. So, I mean, I'm pretty sure that you see it right now, but just in case that you have a bit of hard time imagining this, so you can always think in this form, right? So you could say that if A is k times n, exactly the dimension of A, right? Then your gradient of r hat with respect to that A is going to be taking that particular gradient, the partial derivative of your r hat with respect to every single entry, right? So like what PyTorch does for you, it doesn't even think of a matrix. It's going to think of a big tensor, right? But you don't care, right? If you have a giant tensor, it's going to have lots of variables, right? If you compute a function out of this tensor, then the gradient of that function with respect to this tensor is partial derivative of that function with respect to every single entry, right? And if you get from one giant tensor to another giant tensor, again, the gradient is the same thing, right? So you go after every single entry inside the output tensor, and then you take the partial derivative with respect to everybody in the input tensor, right? So you can always imagine, like, extend your imagination about the larger and larger gradients. This is basically what PyTorch does for you. So you don't give single one-by-one data, right? You give a batch of data to it, right? And it's going to compute the whole batch together, right? So it's going to look at the batch to be one giant tensor, and then it computes the gradient immediately, right? OK. Now, this is the kind of gradient that we are looking for. And let's try to see how we can compute this gradient. One single point, I mean, if you want to, for example, use a gradient descent to update this A, you eventually use the same gradient, right? So you would say whatever my A had been, I'm going to subtract it from the gradient, right? And you keep on going like this. So the gradient is doing the same thing as the gradient with respect to a vector, a gradient with respect to a scalar. This is the same thing. So always A and its gradient are going to be of the same dimension. You can always do this operation on them, right? So, yes. Yeah, it's missed here. There should be a learning grade, of course, yes. Now, what I want to do, I want to get from this r hat, this gradient of r hat with respect to y, I want to get to now what is the gradient of r hat with respect to A. Now, again, we can do the math, but let's see if we can just figure out how it works. So let's say that I have this guy. y equals a times x. Now what I want to compute, I want to compute the derivative of y with respect to a, right? So dy with respect to dA. If everything is a scalar, what should be that guy? It's going to be x, right? It's going to be x. Now what do you expect to be the gradient of y with respect to a? This is going to be x, right? So again, like what I explained in another question. So you might define the gradient different way, and this gradient should be, for example, a giant tensor, right? But that giant tensor are going to include only entries of x, nothing else. Anything else is going to be 0, right? So it's fair computationally that I say this gradient is simply x. Okay? Everybody's clear? Now, let's get back here. So here, the gradient of y with respect to z is simply x, right? Okay. What is the dimension of x? If a is k times n, what should be x then? N, right? So this matrix, vector should be n-dimensional. Now, next thing, if I want to compute the gradient of r hat with respect to a, what is the dimension of that guy? Gradient of r hat with respect to a. What is it? It's a matrix, right? What is the dimension? Exactly like a, so it's going to be k rows and n columns, right? So it's going to be of this form, right? Now, I have one n-dimensional vector. I have one k-dimensional vector. I want to end up with this matrix, which is k by n, right? How can I multiply two vectors to get a matrix? Outer product, right? So I'm going to get this guy, do the outer product with this guy. This is going to exactly match the dimension that I want, right? So how can I write down this gradient? Gradient with respect to z? It's going to be gradient of r hat with respect to y, which is k-dimensional, times the outer product. What should I write next? Yeah, which is x, right? And how should I put x here if I want to make it outer product? X transpose, right? So I have k-dimensional vector, n-dimensional row vector. If you multiply them, it's going to be k by n matrix, right? Everybody's cool? Questions? No question? So again, you don't really need to do the math. You only need to just match the dimension. And once you match the dimension, everything is going to work. But if you are interested, you can keep on writing down the chain rule again, and you're going to end up with the same thing. So you're going to say y is given in this form in terms of a. Now, if I want to compute the derivative of r hat with respect to one single entry of a, then you're going to do the same chain rule. So r hat with respect to every single y that I have times that particular y with respect to the entry that I want, right? And then you do this sum, you're going to end up with this expression. This particular derivative is going to be xn if you have the same row and the same index for y and row for a, and it's going to be 0 anywhere else. So this is going to be of this form. So one particular guy, if you consider one particular entry, then you're going to get the entry of x, which is corresponding to the column, entry of y, which is corresponding to the row, and then you multiply them, which is eventually the outer product, okay? But maybe it's a bit harder to see it here, but intuitively you can always see it, right? So this is the outer product, and what you can conclude is that the gradient of r hat with respect to a is the outer product of that linear or that vector x, which is the derivative of the linear transform, times the gradient with respect to y, right? Again, it's going to make sense because you want to just match the dimension. Everybody's cool? Questions? No question? OK. So that's it. Now, we have these three different operations. So if you have the gradient up to one point, and I want to move backward, you don't have a problem. If it is a linear transform, you can do it. If it is entry-wise activation, you can still do it. You can essentially move backward on any deep neural network, on any MLP right now. Okay? Just to show you that, let's just write down the general MLP and see how does the backpropagation look like here. So if we want to move backward, so this is the kind of presentation we gave at the end of the forward propagation for MLP, right? So you're going to put your data X. That X is going to pass through a linear layer. It's going to give you the first soft output. You activate it, right? So it's going to be the activation. Then you get your next output, or the output of the first layer. You're going to again do the linear transform activation. You keep on going till you get to the output, right? Now, once you are over with passing X through this network, then you can write down the whole computation graph in this form, right? So X is the variable, which is the data at the very beginning. Then it's going to pass through this computation to give you Z. Z is the soft output, then you're going to get activated. So you have these variables in this network. Every single of them is depending on the other, right? And what you want to do at the very end, you want to just compute the loss, right? So you are going to get the output here, and then you give this output to your loss function along with the true label, right? You compute the loss r hat. And the thing is that you want to compute the gradient of r hat with respect to what? Not x. X is the data, right? Weights, right? All of these weights. Weight of this layer, weight of this layer, so on till the weight of the first layer, right? So you want to do that, right? So we can eventually do it exactly like what we did in the local operations. Let's start with the first thing. So first of all, as I indicated before, when you want to compute the gradient on your computer, you're supposed to do the forward pass, right? Because your neural network is supposed to pass that X through every single layer to get the value for every single of these middle variables, right? If you don't know the middle variables, you cannot move backward, right? Because for every single of those local derivatives you're computing, you need to know those values, right? So you first have passed your data through all the layers, and then you got your loss. Now the thing that you want to do, you want to compute the gradient with respect to weights. Let's start with the very last weight, right? So if we just move backward, this is the first guy that we're going to meet. And how can I write down the gradient with respect to this particular weight matrix? Well, this is a combination of those local operations that we had. So what can I say? I can say that, OK, I don't care about anything before y, L, because eventually WL is going to only show up after this, right? So I can simply cut my neural network here, right? So I would say whatever the value of YL is, then this is going to go linearly through this guy, give me the next thing activated, and finally computing the loss, right? So for me, what I want to do, I want to just move backward on this neural net, on this computation graph, right? Now, what is the variable that I want to take the derivative with respect to? WL plus 1, right? So is WL plus 1 a computing variable on this graph? No, right? This is on the edge. We want it on the circle, in the node, right? But can I just replace it in the node? Yes. I mean, ZL plus 1 is this matrix times y, right? I can replace this matrix inside the node and put y on the edge, right? Again, the matrix times y is ZL, right? Everybody's clear, right? So I can do it, that's going to be fine. So I can just take this variable. This is my variable, but I can simply use this fact. My ZL plus 1 is WL plus 1 times y. Right now in this graph, YL is the variable, right? But I can treat this guy as the variable. YL is going to be the transform, right? So this is going to be equivalent to what I had there, right? WL plus 1 is getting multiplied with YL, is giving me ZL plus 1, getting activated, YL plus 1, passing through loss, giving me the sample loss, right? Now I want to compute the gradient. What should I do? I should move backward. What is the first gradient that I need to compute? R hat with respect to YL plus 1. Can I compute that? This is the first thing, right? R hat with respect to YL plus 1. Can I compute that? Can I? Yes. Why I can? We have the loss function, right? We have the loss function. We can write it down, take the derivative, right? With respect to every single entry of y, right? So you can do it. Say loss is, for instance, v minus y squared, right? So the gradient is going to be 2 times y minus v, right? You can write it down that way, right? So this one you can compute. OK, that's fine. Now, next thing, I want to move backward from this guy to this guy. What should I do? Well, I can compute the gradient of this one with respect to this one, yes? This is an entry-wise operation. I can just take the derivative of f and then compute it at every single guy here, right? So this is going to be the backward pass, right? And then if I want to know what is the gradient of r hat with respect to zl plus 1, then I am going to write it down in this form. This is exactly the first local operation we did together, right? Again, I don't expect you to just write it down by heart immediately, right? The key point here is that you get this feeling that, OK, computing this gradient is possible, computing this gradient is possible as well, and I can figure out how to multiply them, right? So now I got this gradient. I multiply it entry-wise with this gradient. I now have the gradient with respect to this one, right? Now I want to know the gradient with respect to this guy, correct? So you can think about whatever you have after this as just one giant gradient, right? Coming directly from r hat to this node, right? So this is the gradient of r hat with respect to zl plus 1. You have it. And the next thing you want to do is to just compute the gradient of r hat with respect to w, right? What would it be? It's going to be that gradient multiplied with the gradient of zl plus 1 with respect to w, right? What is this gradient? It's proportional to yl, right? So it's going to be proportional to yl, and you're going to figure out how you can multiply it. We did it today together. It was an outer product, so you simply do the outer product here. But if after a few days you forgot it, is it still OK? You know that this is going to be proportional to yl, right? The only thing is that how can I multiply it? Well, it should be a multiplication which keeps the dimension right? So I am going to get this gradient with respect to wl plus 1 simply by multiplying these different gradients, right? And you have the gradient of the whole weights together, right? So if you want to update this matrix, you get this matrix, you get that gradient, multiply it with the learning rate, and subtract it from this one. This is your new weight, right? Everybody's cool? Questions? Yes? Y, Z, and W. I mean, of course, you know the dimension of Y, you know the dimension of Z, so you can say what is the dimension of W, right? Yes. How you don't know? I mean, Y is the number of, is like one of your hidden layers, right? You do know what is the number of neurons, right? So you know what is the dimension, right? You always know it, definitely. Yeah. Yes? Yes. Yeah, I mean, the key point is that, I mean, you can think, like, if you want to think computationally, you can think about a general form of product, right? And this is how the computational graph is working. So those outer inner product, entry-wise product, are the things that we define it. Right? At the end of the day, when you have two objects, you can multiply them to build a new object of your choice with a specific dimension, which is fitting those dimensions, right? So in the example here, for instance, if y is, I don't know, I told you this matrix is k by n, right? If y, instead of k, here is, I don't know, some other dimension, 3, right, which is different from k, right? Then, of course, you cannot do that, right? But as long as this guy is k-dimensional, this guy is n-dimensional, you can come up with that product, right? And given the target object, you can always, find an algorithmic way to just do the multiplication, because your computer is thinking entry-wise, right? So you're going to look at that tensor. This entry is connected to this and that. I'm going to multiply it, right? So this is the way that it happens on your computer, so your computer doesn't get confused about that. But for us to just show it compactly, we need to just come up with one notion of product. At some point, like when we get to CNN, I'm going to drop all of these stuff. I'm going to always show a circle. So gradient 1, circle, gradient 2, it means that you just multiply them. And what is the multiplication? Your computer is going to figure it out, right? So just right now to just match your background on linear algebra with what is happening on the neural network. So everybody's cool? Do you see how we compute this gradient? Now, what if I want to move backward further? What if I want to compute the gradient with respect to WL now? What should I do? Well, I can do the same thing, right? So I can again go back to this layer which has Y, WL is showing up there, right? I can cut from there, and I can try to just move backward from very end towards that particular place, right? And then I always do these local gradients, multiply them, till I get to that gradient that I want, right? So this is the idea. So you can always cut your network exactly where your variable is. You can exchange the weight with the variable on the computation graph, and then you have a new computation graph. The very input is what is your target variable. You can move backward on that one, right? So that's the case. For instance, here, this was the network that I had, right? YL multiply this, giving this. And then what I want to do, I want to just take the derivative with respect to WL, right? So in the original graph, if you look at it here, let's go back here once, here, right? So you would say that, OK, I have this ZL, and there was this YL minus 1, which is multiplied with WL, giving me ZL, right? And then you can cut it up there, right? And then you exchange WL and YL minus 1. So this means that on this graph, you are going to have up to YL, right? And then this guy is getting to get multiplied with YL minus 1, giving you ZL, right? And afterwards is everything as before, right? Now, the only thing that you need to do is to just move backward in this guy, right? So how can we move backward? Well, we already have moved backward, right? When we wanted to compute the gradient with respect to this guy, right? We already moved backward up to this point. So we don't need to start from scratch, right? We just keep on from where we stopped, going further backward, right? Now, if I want to get backward from this guy to YL, what should I do? Gradient of ZL plus 1 with respect to YL, which is going to be to contain entries of this matrix, right? So we did it in the second local operation, but again, you don't really need to care about the form of product you are doing, right? This is a linear transform. The backward path is going to be, again, linear proportional to that W, right? Now, I am here at YL. I want to move backward here. What should I do? Partial derivative, and the partial derivative is simply derivative of this activation, right? So it is going to be f dot. And I can always multiply. So whatever I had here, I multiply it to this guy, I get the gradient here. And then again, whatever I have here, I multiply it here, and I'm going to end up here, right? So now, one trick and one implementational trick, I want to say it here, but don't confuse yourself. This is just pure computational, implementational trick, implementational point. And that is that this YL, right? This is the output of your layer L, right? After activation. But if you remember, when we wanted to just move forward, when we compute this activated thing, then we add one dummy one, right? One dummy one, and then we move forward, right? Because we wanted to just take care of the bias, right? Now that we are going backward, we arrive, of course, at this dummy 1. Do we need the gradient with respect to this dummy 1? No, this is always 1. This is a dummy variable. I don't need it, right? So when I move forward, I add it, right? When I move backward, I just drop it, right? So when you compute this guy, if you want to come back from this one to this one, you have one extra entry, right? And that extra entry is the dummy 1, right? So you can drop that. So this gradient with respect to YL0, which is always 1, right? You don't really need it. You can throw it away, right? But don't confuse yourself. It doesn't impact the whole process at all. This is just a tiny implementational thing if one day you want to implement it from scratch, right? In the way that I explained, right? OK, yes? This is not gradient with respect to bias. This is gradient with respect to the dummy 1, right? The bias is the weight, is here inside this guy, right? You compute that. No, you compute that. Actually, you need that one, that y, because that YL0 is showing up in your gradient computation here, right? It's not showing up when you are moving backward, because gradient with respect to that dummy 1 is meaningless, right? And if you remember the graph we had, this 1 was not connected before, right? In one layer, you just put 1, and you just connect it to the next layers, right? So it's not connected backward. There is no gradient there, right? If you even keep it, and you try to figure out the dimension by adding one dummy thing here, the gradient connecting that one to the previous one is always 0, right? So it's not going to impact. Yeah. But with respect to bias, we have it still. It's inside the weight. I mean, this is the whole purpose of adding that one, to just don't think about the bias separately. Always think about it as a weight. OK? Questions? No question? OK, so once you do that, then if you want to just compute the gradient with respect to this guy, again, you have the gradient up to this point. Well, again, you can multiply it with this local gradient. You compute the gradient with respect to this weight, right? And this is going to be the case for every single layer. So for every single layer, you always have been done the backward pass up to the next layer, right? And then you just need to do these 3 operations in order to get to the gradient with respect to the previous layer. OK? Questions? So, moral of the story, you start from very end. You have this computational graph described by your neural network. You just need to know these links which are moving backward. And all of them are given with respect to the weights that you already have, the derivative of your activation, and the values you computed in your forward pass, right? And you can write down those guys, and you can compute the gradient with respect to anything that I want inside this neural network. OK. Questions? No question? OK, is it OK if I just take extra 5 minutes and then we have a break? So just to finish this backpropagation algorithm. OK. Now, one thing interesting about this whole process is that if you write down the way that you compute the gradient, you're going to see that this is exactly dual to the way that you compute your forward. You do your forward propagation. And this is why we call it backpropagation, because it's like you start with data, you pass it forward, so you propagate information over your network, and then you just do the backward pass on the computation graph, which somehow passes some information backward through your network. Okay? To see that, let me just do this simplification in the notation. So the gradient of r hat, we are always computing gradient of our loss with respect to something, right? And then I am showing the gradient of r hat with respect to yl. I'm showing it to be yl dash, and the gradient with respect to zl to be zl dash. Okay? Now, these two guys are different things, right? One of them is your variable. The other one is the gradient of loss with respect to that variable. The only thing that they have in common is that they have the same dimension, right? Dimensionally, they are the same, but there are 2 different things. One of them is gradient. One of them is the information you pass forward, right? Everybody's cool, right? OK. If you do that, then you can actually write down all of these products step by step using this notation. So for instance, you would say that the gradient of r hat with respect to last layer is going to be the gradient of your loss. And then the gradient with respect to the soft information is the gradient of your, with respect to your output times the gradient of the activation. And you now, this is the initial thing that you do. So you first compute this gradient based on your loss function, right? Then you do this sort of, backward activation to compute the gradient with respect to z. And you keep on repeating the same process for every layer. So the thing that you do for every single layer, you're going to get the gradient of that particular weight of that layer to be the outer product of the gradient with respect to z times y, right? So you're going to get the gradient with respect to the soft information. You multiply it with respect to the gradient of the information coming from the previous layer, okay? So it's a product between them. This is the outer product. As I said, you don't care about how exactly you compute that or implement that specifically. But the key point here is that you can write down this gradient as the multiplication of these two. And then you have this loop. So every time you have this particular gradient of the previous layer, next layer, moving backward to the previous layer. And after doing this, you drop one dummy variable, and you keep activating, right? So you just multiply it with the derivative of the activation. So when you are going forward, you get your information. You do linear transform, you activate. Linear transform, you activate, and so on. When you are moving backward, you do the gradient at the output. You do a linear transform, this guy, right? Line 3, right? And right now, forget about that drop. And then you just do one backward activation, right? So you multiply it with the derivative of your activation function. Again, you do a linear transform. You multiply with the gradient of the activation function, right? And you keep on going like this, right? Till you arrive to the very, very beginning. If you arrive at the very, very beginning, now you have the gradient with respect to every guy there, right? And if you want to compute the gradient with respect to any weight matrix, you just need to know the corresponding z and y, right? Which y went to this linear layer and which z came out of it. You just multiply them. You just take the outer product. This is the gradient with respect to that w. Okay? Everybody's clear? Questions on that? No question? So if you write these guys down next to each other, you're going to see that they are exactly the same thing. And this is why we call this algorithm backpropagation, because this is exactly the same process that we do in forward propagation, but backward with gradients, right? And this is going to help us compute the gradient with respect to whatever we want. So in the forward pass, the information is going, so it gives information to the nodes, to the neurons, values to the neurons. And these values are able now to compute the gradient. So these are the kind of information moving backward on your neural network. And you can, as I told you, you can write them next to each other. So in forward propagation, you start with the data. In backward propagation, you start with the gradient of the output, right? And then every single layer, you're going to add a dummy thing. You do one linear transform. You activate. Here, you just reverse whatever you have done, right? You do a linear transform. You drop that dummy thing, and then you activate again backward, right? But with activation, I simply mean here multiplying with the derivative of your activation function, right? And then here in the forward pass, you're going to just report every y and z. Here, again, you just need the gradient with respect to every z and y. And then you can compute the gradient with respect to the weights, right? So essentially, you don't really need to worry about the matrices in between anymore, right? So if you know those hidden values in your neural network, and you can compute the gradient with respect to them, then that's enough. This is the only thing you need, because any other gradient is written in terms of them. Questions? No question? So PyTorch is doing this for you, right? But like old days, people had to do it from scratch. And I put you one paper. One of the authors is Geoffrey Hinton, the CS professor, the one who won the Nobel Prize. And he was one of the guys who initially developed the algorithm was very well known. that you can, of course, use chain rule to compute the gradients, right? But writing it down in the systematic way that it explains that on any architecture you can simply move backward, well, it was not very well known. And then one of the initial works was the one which I put on the course page. You can take a look at that. This is where they explain, okay, you can do it. Look at this. This is dual to the forward propagation of the information. And it doesn't matter how deep the neural network is. We can always compute the gradients, right? But it doesn't mean that people say, oh, very well. Like people say, then what? You want to use gradient descent? It's not going to work, right? And they took like decades that they could convince the other people that it's really working, okay? But this was one of the key observations that they did. At some point in the literature of AI, people, whatever architecture they developed, they had to write down the backpropagation for it as well. Like, for example, LeCun, when he suggested this convolutional network, LeNet, he also developed the backpropagation for it. He said, like, you can backpropagate over it. And this is really the case. I mean, nowadays you don't do any new architecture because pretty much any functional operation, we are already having it. But if you one day come up with one particular new operation in the neural network, you're supposed to show that you can move backward on that. If you cannot, then you cannot compute the gradient. You cannot use gradient descent. You cannot train that architecture, right? So everything works because of this algorithm. Okay? Questions? Now, as I told you before, backpropagation, what it's doing is basically just computing the gradient for you. But the gradient is the only thing you need to train this neural network, right? Once you know the gradient for every single sample, you can compute it for multiple samples. You can average all the samples that you have. You can average it. Once you average it, you have the gradient of the risk function, and you can update the weights of the risk function, right? And you keep on repeating this over and over and over till your risk function or your weights somehow converge to some values, not changing too much your risk function. So the whole idea, I mean, you wanted to do the gradient descent. And if you want to do the gradient descent, you can think of all of the weights in all these layers to be initially some random values, right? And now the thing that you want to know what is the gradient of the average loss, right? Which we called it empirical risk, right? You want to know what is the gradient of that empirical risk with respect to every single of those weights to update these values, right? What you can do, you can start from the first sample, so you get your first sample, you pass it forward on your neural network, it goes as the input, goes towards the end, you have all the values, then you just do backpropagation, right? So you backpropagate over the network to get the gradient with respect to all the weights, right? But this is the gradient with respect to all the weights for that particular sample loss, right? Computed at that single sample point, right? Now you have B different points inside your data set, so every single of them goes forward, comes backward, right? Every single of them. So if you have 1,000 samples, 1,000 times you go forward, backward, right? And then you compute the gradient with respect, or sample gradient for every single of them, right? Now, you have these B different sample gradients, right? All of them. You're going to average them, right? If you average it, it's simply equivalent to just computing the gradient of the empirical risk, right? So the next thing that you're going to do, you're going to compute the mean value, the average of these guys, right? Over the data set that you have. And now you're going to update your weight, right? This is one iteration of the gradient descent. You see it, right? This is one iteration. So if you do one iteration with a batch size of, say, 100, meaning that you just consider 100 samples, then basically you go 100 times forward, backward, and then you have 100 sample gradients, right? You average those 100 sample gradients, you're going to get one average gradient. You update your weights, right? Now you have new weights. You want to update once again. You're going to get the same sample points. You pass it forward, backward. Again, you're going to get a few new sample gradients, average them, next gradient, update, go on, right? Everybody's cool? You see that, right? Now, the key point is that you can do it by parallel processing, right? So on your computer, PyTorch does not really take every sample and go forward, backward, unless you're using, I don't know, some 8086 processor still, right? So the new processors have multiple cores, right? What they do, they're going to say, OK, the first core are going to take care of these samples. The second core are going to take care of these samples, and so on. And since the network is not going to change before you update it, so the weights are the same for every single sample, you can do it in parallel, right? So you can benefit from parallel processing. X's go in, they compute at the same time, and then they come back, right? And you have all the sample gradients together, you average them, right? This doesn't change the fact that your computer practically is doing 100 forward, backward processes, right? 100 forward, backward propagations, right? The only thing is that it can do it in parallel, right? Because it has good processors with multiple cores, right? So, but at the end of the day, you are exactly doing as much as samples that you have forward, backward propagations, and you do one update. And if you do, I don't know, 10,000 updates until you converge, that 10,000 times this b is going to be the number of times you have gone forward, backward on your neural network.